thank you very much for joining us here today. You are in the right place if you're here for our webinar on thermal considerations in PCB design. So today I'm honored to introduce to you Bill Dempsey, who will be our presenter today. And Bill is the owner of Redwire Enterprises in LLC in Texas. He's an electrical engineer with more than 30 years experience in development of circuits for telecom, aviation, and in LED lighting. And that's one of the things you will see here today in one of his examples. So in addition to designing rather complex boards, he's also able to provide thermal analysis to ensure that the enclosure and the boards meet thermal requirements of his customers. So without a further ado, please welcome Bill Dempsey.
Well, thanks everyone for joining. I appreciate that introduction. Let's get started right away. So today, we are going to look at PCB thermal modeling from a PCB designer's point of view. And we will be using SOLIDWORKS flow simulation throughout this seminar. So a couple of things we need to keep track of. We do have a question and answer during the presentation and also at the end. So if you would please submit your questions on your panel during the presentation, then that way we can collect them at the end and we can address those. Okay, so let's start with a polling question. So why are you attending this webinar?
So interesting enough, a lot of people are attending this webinar, Bill, because they want to better understand the thermal issues of PCB, 84%.
Wow. Wow, that's very interesting. So that's perfect. That's what we're going to address today. So the objectives we're going to show you, as we just said, the thermal analysis for PCB designers. We're going to also kind of go over the capabilities of CFD software if you're not familiar with it. And then we have some real world examples. We will be showing you some live out of SOLIDWORKS as well as some screenshots. And then we're going to do the wrap at the end. So there is a little bit of nomenclature that you might hear us say during this presentation. So just to review, if you hear ECAD, we're talking about schematics and your layout tools. When we say NCAD, it's your 2D, 3D mechanical design tools. And then CFD, which we're focused on today, is the computational fluid dynamics. And that's what we use for looking at the interaction of fluids and solids. So you can see over here on the right some fluid flowing through a pin-field heatsink. So what's going on out there? You know, today, these team sizes are getting smaller and smaller, and everyone's getting asked to do more and more. And PCB design is so integrated with 3D mechanical design. The tools that you use today, they all offer 3D view, but there still seems to be a barrier between PCB and MCAD tools. They're independent, and you know, people are not really bridging them. So it really makes sense for the designer to gain knowledge in the 3D MCAD space and take advantage of the integrated tools that are out there. So we're going to do another little poll here. We are very curious, how are you currently addressing your thermal issues?
It appears most people have chosen B as an answer, making educated guesses. And quarter of the folks answer paper and pencil calculation. Interesting enough, 3% said leave the chance, and 4% said consider it as someone else's problem.
Well, so I'm not surprised by those numbers. In fact, it sounds like some of the attendees pre-read this presentation, because that's actually what I find as well. So let's talk about the problem, and most of you guys know this, but just to kind of review, you know, the proper thermal design, it impacts in so many ways. So we've got obviously the functionality of your product, the cost of your product, the weight, the reliability, and sometimes you don't think about this, but the customer experience, and that can be several things. One thing is obviously my product is too hot, it blows hot air on me, I don't like it. Another is the experience is, you know, the product doesn't work well, it burns up all the time. So customer experience is one of those things that we don't really often think about up front, but thermal has a big impact on that. So historically, you know, a lot of engineers use standalone analytic tools, and data still gets passed around with zip files and emails and server files. And those decisions that are made are not always passed around correctly. So, you know, with a simplistic system, you know, a lot of us know there's a well-known set of equations. We use a spreadsheet or some hand calculations. But when we get to a complex system, there's tens to hundreds of heat sources out there. And, you know, you really need a computer to help crunch those numbers, and it gets a little overwhelming. So how do we even go about choosing a CFD tool? There's so much that's out on the market, and you know, I've got listed some of the most popular vendors that are out there. But there's some things you need to really think about. So you want a tool that's streamlined. You want a tool that flows between each of the parties involved. You want a tool that is highly integrated. You don't want to develop something in one tool and then duplicate it in the other. Non-native tools, they generally have a longer setup time, higher learning curve, where you're learning multiple tools. And the last one here that we pointed out is the fear factor. This is something I see in a lot of companies, is that the engineer, it's overwhelming to use a tool. You don't want a tool that's difficult. You want an easy learning curve. You want good training. You want that tool to help you. And, you know, when you buy the tool, you want to use it. So for me, you know, as we talked about at the beginning, I got into flow mostly from an airflow perspective for hobby reasons, and then found, you know, the direct application. But I wasn't sure when I started, you know, what tool I should use. So I did my own polling, and I found that a majority of my customers were in SOLIDWORKS. And for the same reasons I just presented, you know, I needed a tool that would integrate directly with them. And I found that a flow simulation tool within SOLIDWORKS gave me what I was looking for from a CFD perspective. So with flow simulation, you can do all kinds of heat transfer. You know, conduction is your basic style of heat transfer. Convection, and that means both natural and forced. And radiative. So, you know, the tool offers everything we need to get started, but it also has an extensive library of things. So, for example, it has a fan library, and that is huge. You know, that reduces so much time surfing the internet. You know, data is right in front of you. That's a great IC package library, what we call a solid model library, and a 2-resistor model library. And we'll go into a little bit more detail later on that. It has a thermal interface material library, heat pipes, thermal electric coolers. And then for PCB analysis, which is what we're really focused on today, it has a high list of features. So we can look at things, device temperature, the physical PCB heating, touch temperatures. We can do both transient and steady state, so we can look at how long it takes to reach the temperature, or we can look at what the final temperature is of a device or a system. Another thing too, that's this is where it gets difficult and overwhelming, is when you look at nonlinear effects of thermal contribution. It's very difficult to solve on a simple equation. Another thing too, when you're doing thermal analysis, feeding the thermal data into your reliability calculation helps you predict a better MTBF. So you actually would, you know, take the results of this and feed it to that tool. Another thing too that you can do with this tool is you can do thermal stress. Now you would use a SOLIDWORKS simulation tool to import the data from flow, and then look at the stresses on the PCB board. We also have an extensive fan library. We can look at duct sizes, perforation sizes, air speeds. When we're doing heat sink design, and it's completely arbitrary shape, you look at your natural, forced, radiative, and solar loading. And that's something that gets overlooked a lot in a lot of systems. If you're doing a system that needs to be installed outside, like say on a cell phone or on a building rooftop, if you don't do the proper solar loading analysis, you can end up with a big warranty issue. The nice thing is Flow has an extensive geographic library in it. So by location on Earth, time of year, and the operating time, you can actually look at the solar contribution. Another thing too that it offers is Joule heating. So this is when we look at the thermal effect of current flow through conductors. And that gives brace temperature. We can look at the effectiveness of thermal vias. We can look at fusing, either intentional or unintentional fusing. And lastly, it is a parametric modeler, so that allows us to do a high number of what-if scenarios without having to manually enter all of the conditions. We can use a parametric tabular input, and then we can feed that into the simulator. And such examples like I listed here, like you might want to vary fin count or fin orientation, number of fans, the size of the fan, perforations, duct sizes, etc. So the list is very long, but that's just kind of an overview there. So let's get into this a little bit deeper. One of the things when we talk about the flow, so we're going to focus now on SOLIDWORKS flow simulation. So for PCB flow, there's a couple of steps we need to think about. So one is we really want to do our PCB design, get started in our native tool. We want to export that into CircuitWorks, which is integrated into SOLIDWORks. And you can see that in this flow on the bottom here if you follow along. CircuitWorks is used to convert the external format called IDF into a realistic 3D model. And then from there, we can go straight into flow simulation and start our analysis. The nice thing is the flow is reversible, and we can go back with any changes we need to make in SOLIDWORks directly back to the PCB tool. So some advice, keep it simple. You know, models do not have to be beautiful or highly detailed. The more they are, the more the setup, the longer the more complex the simulation can be. And oftentimes the accuracy is not improved. So you need to add detail where you find there needs to be more detail, but generally you start simple and build up from there. So first example, this is a microprocessor board and a chassis. This is something you might have encountered. So here we have a problem statement. We've been asked to design this new microprocessor board, and you're asked, well, will it work in our new chassis? Because the power supply vendor has given us a rule that this power supply can't go above 50 C. But we're told we have to run at 40 C. So what we're looking at here is actually the model we're going to be examining in here in just a minute. So we have a metal cage around a PCB, and we've got a fan attached to the wall. So we're going to look at with and without fans. We're going to look at the heat that's conducted through the board, the convection, and different fan sizes. So as I said, we start in the PCB world. So this is just a top view picture. You can see outlines and such. But since we like pretty pictures, this is our PCB tool has generated this 3D image. So this is still in the PCB world. And from here, I can export this directly into SOLIDWORks. And it brings it in. Now, what you're looking at, you'll see a slight difference here, but this is SOLIDWORks models that have replaced the step models that were in the previous view. So I've got a nice detailed view, and you can turn on photorealism and make it really pretty. But when I'm doing my simulation, as I said earlier, I got to keep it simple. So what I have done is I've replaced my models with my simulation model, and those look like bricks. And they're colored for the type of component they are here. There's so connectors are blue, and the power supply is orange, and the ICs are green, etc. So that's just a color thing that I set up in CircuitWorks. And after I brought it in to SolidWorks, what I need to do is I need to start assigning the heat loads. And so, you know, I'm the engineer in this case, but if you're not, you would get the data from your engineer. And in this case, we have, like you see in the upper corner here, I've got a heat generation rate of 2 watts on my power supply brick. And as you kind of go around the screen, you can see the different power that was applied to each of the components there. And then in the tool, and again, we're going to show this in just a second, but I need to set up my materials, tell it what kind of material it is, and then apply my heat sources as I just showed. And when I've done, I can look at the results. So what I'm doing is I'm doing step by step. I like to start simple. I like to check my work and make sure that my initial results are consistent with my expectation. So in this case, again, we're at 40 C ambient, and you can see by the color chart that the cooler temperatures are blue and the hotter are red. And as you go around, you can see these different callouts I've left on the board. But I noticed right away that the power supply brick is at 61 degrees, and that's above our expected. We're supposed to keep it at 50. So things look good, and I want to step up the simulation a little bit. So I start running my what-if scenarios. Well, the first thing I thought of was, well, what if I just slapped a heatsink onto this guy? Would it work any better? So in natural convection and free air, I notice it really doesn't work much better. So sometimes adding a heatsink, if I don't have the right airflow across it, it's not really adding any value. In this case, you see the temperature's only reduced to 58.6 from 61. And when I put it inside of a box, you can see that there's swirling going on, but I still don't have a fan, and things just aren't looking that good. I can see colors up in the 60s again, and I see here I've looked at velocities. But ultimately, when I put the fan on, I find, and this is that design running live in SolidWorks right now, and hopefully you guys can see the airflow swirling around through the chassis. So this is one of the advantages. This tool shows me right away I've got circulated air, and I may not want that. I might want to put some ducts in. But one thing it has shown me is that my temperatures, and I'll show you that in just one second, is that the temperatures achieve a result which I'm okay with. But all around, I can look at my design. I can see how air is flowing. You can see air flowing through the fan, swirling around. The nice thing is I can probe this, and I can put temperature probes in and look at what things are doing. So we will get back to that in just one second. So here you see that exact same model running. And here I took a screenshot of the temperatures on the board. Well, now look, the heat sink is down to 48 degrees. I've got a little heat rise here, but this is only 14 degrees above the PCB. PCB is at 40 degrees, 40.8, etc. So in under an hour, I was able to look at all these variations, and I was able to quickly determine, yes, I could use a fan. If I didn't add a fan, the venting that I had proposed did not work. The reason being that the flow is in the wrong direction. The flow was coming into the box, but not across the heatsink. And by adding a fan, I was able to reduce my power supply brick from 61 to 48 degrees. So moving on, I want to show you a couple of different examples. This is a heatsink. If you're in the LED design world, you might recognize something like this. This is just a spherical bulb design. And so the goal here is, well, how hot does this thing get when you just set a baseline at 25 C and said without any wind? So again, quickly, I'm able to do the analysis, and I see that the case temperature, the heatsink temperature, is reaching 82.9 degrees C. And that's a function of the amount of power that I put into the LED. Now, that came from the electrical side. I knew how much thermal dissipation was coming from the circuit board. And in front, you're seeing this is actually glass that's heating up. I'm looking at the temperature of the glass. So I now know I've got a touch temperature which is well beyond the safety limit. Also, I've made a note here at the bottom that the heat transfer in this case is dominated by radiation and not natural convection. When you look at natural convection, you can see air is flowing through the vents, but when we look at the speed of it, this is very, very low speed, and when I actually show it working, you can see air is slowly sucking up through the fins, but it's not enough to keep this very cool. And when you break down the design, you find that radiation is actually the dominant cooling effect here. So you probably have a question, well, is it real? So here is a simulation over on the left, and here's an actual measurement. So we actually built, the final model is just a slight derivative of this for the final fin spacing, etc. But that was more for a manufacturing exercise. But the actual measured temperature of the fin in the lab under the same conditions is 81.7 degrees C, and it had predicted, I believe, 83 on the same fin. It's in this zone right here, so it's showing this color, and so extremely close. So if you set up the problem correctly, you can have very, very high confidence in the tool's results. So we also talked about Joule heating earlier, and this is something on the PCB side. It's very important. And again, so what is it? It is the temperature rise caused by current flow through a conductor. And that is really critical when you're pushing a lot of current through a trace. I get asked all the time, well, how hot will it get? And unfortunately, the answer is it depends. I have copper thickness, I've got PCB, stack up, there's so many things. Is there airflow or not airflow? And of course, Joule heating is something you use if you want to determine melting point of a fuse, or would your trace actually act as a fuse? So really, this should be part of your thermal analysis. You know, it's good for, as we said, the trace temperatures, but also you can look at current in electrical vias. You can look at thermal conduction through thermal vias. And you think, well, a via is a via. Well, the definition we're using here today is an electrical via participates in the current flow. So that moves the current from an upper layer to a lower layer or vice versa. A thermal via moves heat in the same direction. So sometimes you need thermal vias, sometimes you need electrical, and you're asked, well, how many do I need of each? Well, the nice thing is with this tool, you can determine that. So let's look at a real case here. What you're looking at on the right is a picture that's actually a connector that straddle mounts a PCB, and what I've done is I've extracted just the copper that's the main power feed. And down in the corner, you see this little black rectangle. That was actually where the customer was extracting all the main power due to their layout. They could only feed current to the one spot. In this particular example, we have 3.3 volts coming in. So what I did is I took that board in and I just removed the connector because it's kind of in the way pictorially. I applied my voltages at the edge of the copper. I set the copper thicknesses. I set the current load, and I added my vias as required. And that's what it looks like when I get rid of the PCB. You can see the vias penetrating top to bottom. Those are standard 8 mil vias. Those are filled vias for this example. So one of the first things I can look at right away is where is the current flowing, and what we're looking at actually is this is a scalar plot of current density. So we can see the current is highly concentrated from the one feed to the output, which is again the black rectangle, and there is feed from the other side, and it does go down and over, and we're going to look at, so this is kind of top view, and that's looking through the top. Copper's been removed for clarity, but you can see currents flowing, but you see these kind of cold zones, as I call them. They're not really flowing current, which is kind of accepted. The current is not wanting to flow out to the corners here. And now when I look at actual temperatures of this, I can actually go back in and I can see, okay, you know, I've got temp rise. The good thing is when I look at the scale, it's very low in this case. And the biggest reason here is that I've actually got a 6-layer PCB, which is dissipating that heat, and I've assigned the amount of copper on the PCB, so it does take that into effect when it's into the calculation when it's doing this analysis. And we can do it with, without, etc. So in this case, we did it with a 6-layer PCB. Something else, when you're looking at the design, we talked about, I said thermal versus electrical. And I've set this scale where white is essentially 0 in the middle, and current flow in one direction, we have around 9 amps per square millimeter, and then minus 8.7. So I'm going to zoom in a little bit here. So you can see current, if you recall, the output was on the rectangle, and we got current flow down, over, and the red is showing it back up. When I look at the other side, I also have current flowing in that direction, but it's at a much lower scale, which is expected. There's higher resistance between the two ports, so the current has to be lower. And then, sorry, if we go back for a second, you can see most of the via field in the middle is not pulling current. If we zoom in really tight, you can see fractional amounts of current flowing. But the other thing now we look at is the thermal result. And so you can see the via field, we have a very even flow of heat from top to bottom. So now what I can do is I can actually determine, do I need this many vias? Because a lot of the current wasn't flowing through there, but if I didn't have enough, I might have had a different result here. And so I can quickly look at the number of vias I need. Maybe, sometimes people think if fewer good, more must be better. Sometimes they don't actually help and they get in the way. So that's the nice thing about this tool. You can do that analysis and be very confident that you have the proper number of vias to carry your current and to carry the heat out of your board. So, done a quick view. We have we go back into SOLIDWORKS in just a minute, but I want to ask you right now, are you seeing what you want to see? Is there more detail you might want to see in a future webinar?
Well, Bill, it looks like more detail PCB and analytics is the winner.
Okay, good. That's why we were here today. That's our primary reason. So I think since we have the time, what we should do is possibly jump back in. Let's stop what we're seeing here just for a second and focus more on the PCB. So I'm going to start with the very basics here for you guys, just to show you a little bit more detail. So I showed you earlier that we had a PCB import. And again, the design was imported directly from the PCB tool through the CircuitWorks tool. And what I have here, so there's a couple things that we're looking at. One is we talked about materials. So each of the components that you bring in need to have some sort of assignment on them. And what we've got here is solids are chosen through a library. Here in this case, I've got my IC package library open, and I'm assigning by type the material of that particular IC. The PCB itself is defined in when I bring it in right here, I've assigned it to the PCB, and that particular PCB is, if I go into this guy, I can actually define all of the parameters of that PCB, how many layers it is, the total thickness. Here I've got how much coverage of copper per layer. So in this case, this is 6-layer board, and I have power planes here and here, which take up most of the area. And these are internal signal layers. So I've gone through, and even down to the dielectric material, this is directly out of the manufacturer data sheet. I enter this in here. So I have what I get. I have a standard 1.6 millimeter thick board. It's a very accurate representation of the PCB material that's going that's being analyzed. So through this, I've set up my PCB, I've set up my materials, and I go in and I apply heat, okay, to the components as required. I could add more heat sources if I need to. etc. I can also do things like applying a heat sink here. I can insert a part here. I can tell it I've got thermal compounds in between the different devices. But this example here is just natural convection, and when I run it, I will just go ahead and just load the results for quickness here. The simulation, depending on how you've really set it up, can take 2 minutes to 20 minutes or more, just depending on the exact example. Something else that's required, if you look in this little list here, there's something called goals. The reason we have goals is when a solver is attempting to solve a problem, if you don't tell it what it's solving for, it will take a generalized assumption of what should be solved. And what that means is it looks at the results of each of the different kinds of analytics it can do, and when it sees those converge to a certain convergence point, it says, I think I'm done. But what I've done is I've said, no, I want you to finish when you see this solid temperature stabilize, this one stabilize. Everything needs to be fully stable so that I get a more accurate result. Another thing that you would want to set up is if you have some high detail areas, we call that meshing. So in this design here, I've set up global mesh and local mesh. That allows me to set up a fine grid in areas that need more detail. And when I'm done, I can see, for example, if I'm looking at, let's see if I can make that show better for your screen. I don't think you have the resolution to see that, unfortunately, in this presentation mode. The surface plot, so here what I'm doing is I'm looking at, well, what, for example, are my solid temperatures? So I've gone in and I've selected in this tool here, I've actually told it, I want to know what is the temperature of this and this, for example. So I put my faces in, I set it up for please display temperature. I want about 35 gradations in my scale, and I can always, of course, change that kind of stuff. I can make things coarse or fine. I can change limits. So this tool allows lots of variability. I can move colors around. This is the after the analysis is done, this allows you to post-process. So we're just post-processing our data. The data set's complete, and I can go in, I can do studies of airflow, I can do all sorts of post-processing analytics. I can export to Excel, etc. So I hope that gives you a little bit better view of PCB analytics. We can answer certainly more questions if you post them into the questions section. I want to jump back quickly to the seminar. So we did the question there, and now is our time to ask the famous question: how would you rate this presentation material?
Bill, it looked like most people found this to be relevant, at least to 3/4.
That's good. So, so we intend to do another series, and if you have some feedback on, for example, if it didn't meet your needs, sometimes we're looking at a variety of audience numbers, and we want to try to keep it simple today. We can go into sort of really interesting analytics in another webinar. So please forward that if that's what you're interested in. So thank you for your feedback. So just quickly, a summary. I mean, my thing is you really should have a CFD tool as part of your design toolbox. That gives you so much more confidence in your design, and you can reduce costs. You can avoid costly mistakes. Is another thing. But it needs to be intuitive, easy to use, and integrated into your workflow. So our goal today is to show you that there is you can use these tools, you can use them quickly, you can get some results that will help you with your design. And I find that SOLIDWORKS Flow is a tool that helps me do that. And as I've shown you, these are the items that I use it for regularly, and it's been a valuable component in my toolbox. The other thing too is that my flow, it's native into SOLIDWORKS, in and out. I've got this great library. I don't have to do a whole lot of hand building of library parts that can slow you down so much. And you know, it's a very easy to use flow. So that ends my presentation. We will take some time to review your questions and see if we can address those right now.
Well, thank you very much, Bill, for the presentation there. So what Bill's going to do right now is he's going to take a look at the questions panel there. So if you have some questions, please feel free to write those in. I already see some really good ones for you, Bill, to mull over while we just give a brief introduction to 9.Connects. So you're here for a reason, and in this particular webinar, you're here to understand the thermal analysis tool or tools that are out there, to also understand what types of tests that can be performed. And hopefully you also understand too that most of us are electrical engineers or come from the electrical side of things. You don't necessarily need to know thermodynamics to do this, right? And a lot of it is just going to be some intuition. Some of them is just going to be some best practices. And the tools are really there just to confirm those educated guesses that we're willing to make or take. Now, as for 9.Connects, we do provide coaching, we provide training, we provide services. But today, just want to let you know that a lot of times when people ask us for services, it's for all the quote-unquote other things like thermal analysis or signal integrity or design for manufacturing or for library management. So if there's something that's causing some issues or consternations in your design practices, feel free to give us a call here at 9.Connects because we do know people like Bill, and we have people on our staff as well who are knowledgeable in these particular areas that tend to be troublesome at times. So for more information, feel free to take a look at our site, 9.Connects.com. I'm going to tell you something. On a daily basis, we're always either updating or we're adding to this website. It's just a continued work in progress. We're happy with putting out there, and there's a lot more things we're going to continue to put out there as well. So go check us out there.
Thank you so very much for taking the time to attend this webinar, and we'll look forward to bringing back some additional webinar related to this thermal analysis.